Welcome, Spesh 1-2 fans, to the first lesson of the next unit, Number and Proof. Now, some would argue that this is the most important unit of the year because, after all, it concerns proof, and proof is how, in mathematics, we're able to assert truths. We don't do them by popularity poll or on the balance of evidence. We form well-structured arguments that compels us to accept the conclusions as being true. No opinion, no preference coming into play whatsoever. Now, on the other hand, some would argue that it's the least important unit because it's not directly part of the 3-4 syllabus. I feature in the former camp. I actually believe it is quite important, and it sets solid groundwork for any future proof you might be doing in mathematics. So let's have a look at the objectives. We'd like to understand and apply direct proof, proof by contraposition or contrapositive, proof by contradiction, and then at the end of this session I'd like you to understand the notion of when statements are equivalent, how to disprove statements using counterexamples, and then we'll leave for another time the principle of mathematical induction. So this session will cover a broad range of the proof techniques that you'll be doing questions on in exercises A to E. Okay, let's begin with statements of implication. So essentially they're if P then Q kind of statements that we have to prove. So we codify it as for two statements P and Q. Double line arrowhead Q is shorthand for P implies Q. So if P, then Q. All right, here's some statements in English. Nikhil arrives at school at 9:05. Then he missed tutorial. Emily has a dog named Snoopy. Then Emily has at least one pet mammal. If Kevin was born and raised in Zimbabwe, then he is African. If Audrey is late for period 1, then she missed tutorial. Now these are all statements of implication, if-then statements. Now, are all of them true? Now, what we're going to do is look at implication statements and look at the structure of proof to hold them as true, or disproof when we look at counterexamples. So just going back up to the Audrey example, for instance, if Audrey is late for period 1, then she missed tutorial. Let's think of a counterexample. Perhaps she was detained by her tute teacher, or she had to see another teacher, or something to that effect. Kevin was born and raised in Zimbabwe, then he is African. Perhaps you might have a different view of what African is. But we'll get on to, these are all non-mathematical examples. Let's look at the context of mathematics. Okay, to explore statements of implication in the context of maths, let's look at this familiar context. So this is a question from chapter 2 of the book, one that I think I've talked about before. And it's indeed a statement of implication. So for the simultaneous equations as you see it, show that x is this and y is that. Classic if-then implication statement. So in this case, the P stands for the assertion ax plus by equals p and bx minus ay equals q. Q, the conclusion, stands for those assertions. X is that expression and Y is that expression. So it's the classic if-then, P implies Q format. So what your job is to take P and show by a sequence of algebraic transpositions that we can arrive at Q via following the correct logical sequence of transpositions. So remember, you're not allowed to involve Q in P. It's all about altering P through a legitimate chain of logic until you arrive at Q. Okay, just out of your interest, you won't be tested on this, but P is called the antecedent and of the implication, and Q is the consequent. Mathematical statements, P and Q, can be thought of as being represented by sets of numbers. So We could think of P as being the set of numbers that satisfy that particular assertion, and Q being a different set of numbers that satisfy that assertion. So what does it mean when we assert P implies Q? So one way to think about it is to understand that any set of numbers that satisfies P must, by virtue of that, also satisfy Q. There's something about the structure of P as related to Q that makes that true. This is neatly represented by our Venn diagram. So if you could think of P as being all the set of numbers that set that makes it true, Q is the set of numbers that make it true, you can see if P is embedded in Q, it means that if P is true, then certainly Q must be true as well. So that's just a nice way to think about it. Consider this example here. So x squared, we're told, is strictly less than 4. Here's an implication, implies x plus 2 must be greater than 0. So one nice way to illustrate this is via a number line. So you can see the blue line is representing all the set of x values that are strictly less, whose square is strictly less than 4. The red line being all x values such that x plus 2 is strictly bigger than 0. And you can see that the blue set of numbers fits neatly into the red, and so that makes that implication true. Okay, here are some other statements of implication. X minus 3 is 4 implies x is equal to 7. X is divisible by 3 implies double that, 2x is divisible by 6. If x is equal to 3, then x squared must be equal to 9. And this is something we'll actually formally prove later. If P times Q, the product of P and Q is odd, then P is odd and Q is odd. Okay. Now, something you might have picked up on is the third example is different from the other three. Okay, so in the first two and the fourth examples, what we can say is the converse is true. That is, if x is equal to 7, then x minus 3 is indeed equal to 4, looking at the first example. So what we've done is changed the order. So what was the antecedent is now the consequent, and vice versa. Looking at the second one, if 2x is divisible by 6, then this implies x is divisible by 3. Again, we'll prove this for you guys later. If P and Q are odd, then it means their product is also odd. Now, that means that the initial statement is true and their converse is also true. And that leads to this idea of equivalent statements. Now, the third example, that breaks down. If we were trying to start with the conclusion x squared equals 9 and prove x is equal to 3, you might have picked up on the fact that that's not in fact true. Okay, so combining P implies Q with its converse, so reversing the order Q implies P, we get the statement P double line double arrowhead Q, which is read P is equivalent to Q. So from the previous slide, we can draw the following statements. X minus 3 equals 4 is equivalent to x equals 7. X is divisible by 3 is equivalent to 2x is divisible by 6. And two integers are odd is equivalent to the product of two integers is odd. Now that's not so obvious, and we will look at the formal proof in a minute, as I said. Okay, it's important to know that the statement if and only if is a synonymous understanding with equivalent. So equivalent or if and only if can be used interchangeably. They mean the same thing. It means that implication goes in both directions. For instance, if A, B, and C are side lengths of a triangle, A squared plus B squared is equal to C squared if and only if A and B are side lengths, the shorter side lengths, and C the longer side length in a right angle triangle. So you might, and there's other many famous if and only if statements in mathematics. All right, so how does an equivalence get proven? How do we establish equivalence? Well, we need to prove in one direction, P implies Q. So we need to, there's actually a proof is two legs or two horns to it, if you will. So P implies Q needs to be established, and then the converse, Q implies P, also needs to be established. When it does, you've got equivalence. So the best way to understand how we can use that term equivalence would be to understand P implies Q and Q implies P in terms of sets. So there they are. So if P implies Q would indicate that all the things that make P Q is a subset of all the things that make Q true, pardon for that. And the converse, if Q implies P, it means all the things that make Q true is a subset of all the things that make P true. Now, for them both to be true, then what conclusions can we draw? That's right, that P, all the things that make P true are also equivalent to all the things that make Q true. So this idea of equivalence is quite a powerful one. It's to say, even though on the surface two statements mightn't seem like they're indicating the same set of truths, in fact, using logic, we can assert that they are in fact equivalent. They are saying, in fact, the same thing. All right, here's an example from exercise 3C that you'll be tackling later. For real numbers A and B, A is strictly bigger than B if and only if A minus B is strictly bigger than 0. Now, what does that mean? You need to understand it. It means that those two statements are equivalent. So it means that if I have A strictly bigger than B, then I can neatly slide along to A minus B must be strictly bigger than 0. Or conversely, if I have the difference of two numbers being strictly bigger than 0, then I can imply that A must be strictly bigger than B. All right, so I'm going to use this powerful connection between those two assertions to prove that, let's have a look at A, to prove that the first, the former, is strictly bigger than the latter. All right, so let's see how this might work. And this caused some problems for students last year, so let's focus on this. So I'd begin by using that equivalence as follows. I'd subtract the 2. Okay, so 5 minus 3 root 2 less 6 root 2 take 8, of course, is 13 less 9 root 2. And I've now got to prove, my aim is to show that that is going to be strictly bigger than 0. Now, okay, let's have a think about root 2. What is an approximation for root 2? If you're thinking 1.4159, etc., then you'd be right. Okay, so I've got 13 minus 9.14159, etc. So if I took a slightly larger multiple of 9 and took it away from 13, so a slightly larger, so let's go to 1.42. So if I went 13 minus 9 times 1.42, I have a smaller number. Okay, so with that in mind, we can say that that 13 minus 9 times 1.42 is definitely strictly smaller than the above, because 1.42 is larger than root 2. I'm taking away a larger number. All right. I can't pull out my calculator much as I'd like to, because to prove it by hand is what this is about. So off on the side, I do my multiplication algorithm, 1.42 times 9. There it is. Ah, nice. 12.78. So therefore, I can assert the next statement. Well, that's it in itself is going to be a positive value. 13 minus 12.78 is strictly bigger than 0. Which leads us to the conclusion that our initial statement was strictly bigger than 0. Therefore, we can show that 5 minus 3 root 2 is in fact a bigger number than 6 root 2 minus 8. Okay, we began with 4 statements, and we noted that 3 out of the 4 were equivalent statements. However, the third one wasn't, and that was the statement that x equals 3 implies x squared equals 9. True, can't fault that, but its converse we could fault. X squared equals 9 does not imply x equals 3, because after all, x could be equal to minus 3. Now we could establish equivalent facts that x is 3 or minus 3 is equivalent to x squared equals 9, but it just goes to show that not all our implications work in the opposite direction. Some are only one directional implications. In fact, really most statements we make are. All right, now, how do you reckon we go about showing that implication doesn't work in one direction or the other? What would be the process for doing that? If you were thinking setting up a counterexample, then you're spot on, because that's how we do it. To show that A does not imply B means just find one example out there where it's not the case, where you've got it's true in the sense of A, but it's not true in the sense of B. So all right, so let's have a look at some specific examples now. So here's one not far from where we were above. If x is strictly bigger than 3, certainly it's the case that x squared is going to be strictly bigger than 9. However, if we reverse that, you can see it's not always the case. X squared must be strictly bigger than 9. Does not imply x is bigger than 3. What's a counterexample? Well, we could prove that almost by logic, but a counterexample is any value of x less than minus 3, of course. Okay, here's another one. X is rational implies the square is also rational, but the converse is not true. X squared is rational does not imply that x is rational. Can you think of a counterexample to that? Can you think of a value of x where the square is rational, but the value itself is not rational? Aha! If you're thinking third, then you'd be spot on. Say root 2 would be a classic example of that. So root 2 squared is 2, certainly rational, but root 2 is not rational, as we've discussed. Okay, two numbers are even, therefore the sum of two numbers is also even. However, if the sum of two numbers is even, it doesn't imply that the individual numbers are even. So think of a counterexample. In fact, think of any two odd pairs. If you add any two odd pairs, isn't it the case that their sum is also even? That'd be right. So, so there's another example where implication works in one direction but not the other. Here's a geometric example. So a quadrilateral ABCD is square implies the sides of the quadrilateral are of equal length. Yes, okay, true. Does it work conversely? Okay, the sides of a quadrilateral are of equal length, therefore the quadrilateral is a square. No, sadly it doesn't. Not so sadly, it's just they're not equivalent statements. Can you think of a counterexample of a four-sided polygon, a quadrilateral where all sides are of equal length, but it's not a square? If you're thinking of a rhombus, then you're spot on. Okay, we've held off thrill seekers long enough. It's now time for proof itself. Okay, how do we prove directly, by contrapositively, or via contradiction? They're the three basic approaches we'll be looking at in this session. Now, of course, as I said, proof is fundamental to mathematics. Our next unit will be running with the idea of proof in the context of geometry, which is an excellent unit to follow on from this one. But okay, so what's common to proof is algebra, after all, because algebra has the ability to generalize numbers. And of course, if we want to assert anything to be true for all numbers, we need to use algebra. We can't just come up with lots and lots of examples that show that it's true. It's not enough. We need to use the general language of algebra in order to establish those facts. Okay, let's have a look at this example of direct proof. If two numbers are even, n and m, then their sum is also even. M plus n must also be even. All right, so how do we use our friend algebra to help us out here? Well, this is something you'll be going to quite a bit in this unit. So it's a useful fact that any even number, I've mentioned this in class as well, positive or negative, can always be expressed as 2 times k or n, choose whatever parameter you'd like, where k is a member of the integers. So anything that's a positive or negative or zero, positive or negative whole number or zero. Okay, so any even number has that characteristic. Think of 18, 18 is 9 times 2. Think of 200, 200 is 2 times 100. 98 is 2 times 49, and so on. So it's always going to be have the feature 2 times an integer, a member of the integers. Now, on the issue of even numbers, it's just conventional actually to call 0 also an even number, so it fits that that general characteristic of being able to be expressed as 2 times an integer. Of course, 0 is also an integer. Now, odd numbers, and we'll get on to these later, have the characteristic they could be expressed as 2k plus 1 or 2n plus 1. Choose whatever parameter you'd like. Could be 2k minus 1. It doesn't really matter. I just like to make things simple and call it 2k plus 1. Any odd number can be expressed in that generalized form. Okay, this is where we're going with our algebra. So we've got n and m. So because of that feature, there are two integers, alpha and beta. So two integers, alpha and beta, such that m is 2 times alpha and n is 2 times beta. Must be true for n and m to both be even. Now let's just add them together. Okay, 2 alpha plus 2 beta, and factor out 2, and now we're left with 2 lots of alpha plus beta. So if alpha is an integer and beta is an integer, then alpha plus beta must also be an integer. Now you might argue that also needs to be justified. Well, it's pretty easy to justify using a number line, if you will. So if alpha is a certain number of places, whole number of jumps from 0, and beta is also a certain number of whole number of jumps from 0, either left or right, if you get to where alpha is on the number line and then you apply beta to it, jumps left or right, you'll also end up a whole number of jumps from 0. That's actually pretty basic, but I think you can take these as true and run with it from there. All right, so what have we established? We've established that if m and n are even, then m plus n must also be even using algebra. Okay, what we just saw was a very simple but important example of direct proof. Proving P implies Q, and that's classically where most proofs are oriented towards direct proof. And what do they usually involve? Well, you work with definitions or transpose to establish equivalent forms from the left-hand side to show that that the truth of P logically entails the truth of Q. Somehow you manage to transform the left-hand side into the right-hand side to show that it logically entails what you're trying to prove, which is Q, from a basis of P. All right, so that's direct proof. Okay, but there are a couple of lesser known alternatives. Now the first one, proof by contradiction, we've actually already seen. So I'll discuss that in a minute. So what you do is begin by assuming the opposite of what you want to prove, that P doesn't imply Q, or P implies not Q. Okay, and then you go and show via valid reasoning that this P implies not Q leads to a contradiction, and so what that means is P, the opposite of that must be true. P does not imply not Q. P in fact implies Q, and that's one sneaky way around the back door that you can establish implication. P implies Q by assuming the opposite of what you wanted to prove is true. Now what we did with that proving root 2 is irrational is we began by the assumption root 2 is rational. In other words, root 2 could be expressed as a ratio of two values, A over B, or A to B, where A and B are co-prime. That is, they couldn't be further simplified. They have no common factors, in other words. And by beginning with that assumption, we went through a series of steps, a series of logical steps where one established the other, and we showed that that led to a contradiction, that A and B couldn't be could be further reduced. They did have a common factor, and therefore our initial statement had to be false. So that's proof by contradiction. So we'll be practicing that for you guys as well. Now the other one, and this is I find this really interesting. It's not very often mentioned in textbooks, but it can be the way to go. It can be much easier to prove things in this way. So instead of proving directly P implies Q, what we could do is start with the consequent Q and negate it. Talk about not Q. And if we find it easier to prove not Q implies not P, then in fact that's a backdoor way of in fact proving P implies Q. So to actually prove not Q implies not P is equivalent to proving P implies Q. A good way to see it is to look at, again, the Venn diagram. If P implies Q, then P would be all the things that make P true is a subset of all the things that make Q true. Not Q is all the things outside of Q. So if we could show that not Q must logically entail not P, then this must be the relationship between P and Q. So we'll look at an example that brings that out quite nicely. All right, finally we get back to this equivalence, statement of equivalence. P and Q are odd integers if and only if their product is odd. The product of two integers is odd. Wow, okay, remember if and only if, we need to prove, it's in fact two proofs for the price of one. We need to prove if P and Q are odd, this implies their product is odd. Also, in addition to that, we need to prove that if the product of two integers is odd, then those integers separately are also odd. Okay, so this is how we're going to go about it. So feel free to pause at any time and have a crack on your own if you want to. All right, so we're going to start with implication in that direction from left to right. P and Q are odd is our assumption. We have to show that that assumption leads to the product also being odd. So the truth of the first entails the truth of the second. All right, so as I said before, this is one way to generalize odd numbers. So 2n plus 1, 2m plus 1, n and m are members of the integers, positive or negative whole numbers including 0. Okay, so quite easy. We can actually do our binomial expansion, our two-term expansions here. And when we do expand it, we've got those four terms, 4nm plus 2n plus 2m plus 1. Now the first three terms factorize nicely. We can take out 2 as a common factor. And we've already seen if n and m are integers, then n plus m are also integers. We'll also take it locked in as true if n and m are integers, then n times m must also be an integer. And again, you could just justify that along the number line. 3 times 5 is 5 lots of 3, etc., etc., etc. So we're not going to get into that level of nitty and gritty. You can take those very, very core number facts as true. Okay, now as you can see, if n plus m is an integer and n times m is an integer, then 2nm plus n plus m must also be an integer, which means p times q must be of that basic form. 2 times some integer plus 1, and that's the general form for an odd number. Therefore, p times q is indeed an odd number. Direct proof, nice and neat. Let's now move in the opposite direction. All right, now let's start with proof in the converse direction. So we're going to start with the assumption PQ is odd, and we need to show that this implies or logically entails that P and Q are both odd individually. So, okay, so if you were to prove it directly, you might start with a statement like this. PQ is equal to 2n plus 1, where n is a member of the integers, and then quickly the ideas dry up. Okay, so if you're ever at that impasse in your proof of equivalence, what you might like to try is to negate the consequent. In other words, to prove by contraposition, or the contrapositive of that implication statement. So how does that work again? You look at the consequent and you take its opposite, or you negate it. So what's the opposite of P and Q are both odd? Well, it would be that P and Q are not both odd. In other words, have a think about what that entails. Either one or the other is odd, is even rather, or they're both even. So there's two possibilities we'll need to explore with that initial assumption that we're going to take that P and Q are not both odd. So P is even, or Q is even, which entails, of course, they're both even. So what we aim to prove by starting with P and Q are not both odd is we aim to prove that this logically entails P times Q must be even. So we're taking the negation of the consequent, and we need to prove the negation of the antecedent, the initial statement. So we're going to take not Q, now I can't use P and Q because they're being used, but we're not the conclusion, and we need to show this logically entails or implies not the assumption. Okay, so all right, anyway, so let's begin. Okay, let's suppose that one is even and one is odd. Because these it doesn't matter what we call even, what we call odd, let's just call P even and Q odd. Okay, so with this setup, we're going to show that the product P times Q must be even. Okay, so P is 2m, where m is an element of the integers. Q, being odd, is 2n plus 1, where n is a member of the integers. So can't use the same parameter. We need to use a different one because, after all, they could be different multiples of those n and m's. So pretty easy to establish, isn't it? So 2m times 2n plus 1, we can take m as a product, and what you've got, because we know sums of integers are integers, products of integers are integers, what we've got is an expression of 2 times the product and sum of integers being an integer. In other words, it could be expressed as 2 times some integer, and what this is established pretty quickly is that PQ must be even. In other words, not odd. Okay, great, very straightforward, and that was just supposing that one of them is even. All right, moving ahead to the second part. Okay, and when both P and Q are even, it's even easier to show that the product of P and Q is also even. As you can see there, it's going to be expressible as 2 times an integer, and therefore it must be an even number. So what have we shown in this leg of the proof? We've shown if P and Q are not both odd, in other words, one or both are even, then P times Q must be even. What does that establish? Notice they're both negative statements. We can turn that round as a positive implication like this. If PQ is odd, it implies P and Q are, if P times Q is odd, then it implies P is odd as well as Q is odd by contraposition. So that's what we're aiming to show in that leg. Now, in the first leg of the proof, of the equivalence proof, we showed that P and Q are odd implies P times Q is odd. And so we have established the equivalence between P and Q being odd integers if and only if the product of those integers is also odd. All right, it's time to look at a question from the exercises, an equivalence statement question from the set questions you'll need to do. In fact, this is one less you'll need to do now. So I'd like you to have a go yourselves. Go as far as you can on your own. You might be able to go all the way on your own. Part A is just start with the right-hand side, expand it to show the left-hand side. Not a big deal. But then B is an equivalence proof. So prove that the assertion m is even implies m cubed minus n cubed is even, and the converse is also true. M cubed minus n cubed is even implies m minus n is even. So show that logical implication goes in both directions for part B. So pause it, have a go on your own. I'll go through the proof when you want to get back to it. You might want to pause and restart as you go. Okay. All right, so let's begin. We're going to prove, so I'm going to take that as a fact in A, and we're moving on to part B. So we're going to move from the statement on the left to the statement on the right. We're going to show that if m minus n is even, it does imply m cubed minus n cubed is even. Now this is pretty direct. Now we've already discussed that the only odd product is odd times odd. In other words, any number with an even factor must itself be even. Okay, so only odd times odd is odd. All right, so as you can see from the above equivalence, if m minus n is even, then we can see m minus n is a factor in m cubed minus n cubed. In other words, m cubed minus n cubed has an even factor via that expansion rule, and therefore m cubed minus n cubed is even. Okay, implication in one direction, not a problem. Okay, our second aim is to show that the converse is true, that m cubed minus n cubed is even implies m minus n is even. Now, I scratched my head for a while on this one, then I thought, well, why not show by contraposition? So what we're going to do, in other words, is take the consequent, m minus n is even, and negate it. We're going to suppose m minus n is odd, and then show that that logically implies m cubed minus n cubed must also be odd. And then we've done what we need to do via contraposition, or argument of the contrapositive. All right, so in other words, that's what we need to show. We've now switched it around. I like working with the consequent originally, so I'm going to make it the starting point by negating it and working on the fact that m minus n is odd to show that m cubed minus n cubed is odd. Okay, so if m minus n is odd, it means that firstly, either m is odd or n is odd, but not both. Have a think about it. Okay, we can do a proof in itself. I've just got the case where both are odd. So m is 2 alpha plus 1, n is 2 beta plus 1. If we subtract the two, we've got ourselves an even number. So, and you can do the same for both even numbers. Subtraction of two even numbers is clearly going to give you an even number. So what this means is for m minus n to be odd, either m is odd or n is even, or vice versa, without any fear of reducing the generality of this argument. We're going to look at m is odd and n is even. Okay. All right. Now, what we need to do is to show that that factor of m cubed minus n cubed is odd. Why does it reduce down to that? Because we know m minus n is odd, that's our assumption, and we know odd times odd is odd. In fact, that's the only product of two integers that lead to an odd number. So really what this proof comes down to is showing that that factor must be odd. Okay, so m is odd. Of course, that means m squared must be odd. Odd times odd is odd. N is even. That means mn and n squared are also even. So at the end of the day, we've got an odd number, m squared, being summed with an even number, mn plus n squared. So if m and n are both even, if mn is even and n squared are even, then their sum must also be even. That's something we showed earlier. But what does this mean? If we're summing an odd number with an even number, the result will always be odd. And there's some algebra to just flesh that out a little bit. Okay, so because m squared is odd and mn plus n squared is even, it means that m squared plus mn plus n squared must be odd, and we're home. It means that m cubed minus n cubed is odd based on the equivalence in part A, and we're done. We've shown what we need to show via contraposition. All right, I just thought we'd look at this last example. It's nothing harder or trickier than what we've done before. It just involves a technique I thought you should be aware of. So you can see some number patterns going on, consecutive numbers, um, alternatively positive and negative equaling a number pattern. So the statement is as follows: if A, B, C, and D are consecutive natural numbers with B bigger than A, C bigger than B, and D bigger than C, then that statement must be true. You have to prove it. Now, they've thrown you off a little bit by using 4 different pronumerals. So how could you make this easier by collapsing those 4 pronumerals to a single one? And the key to this was the phrase consecutive natural numbers. All right, so if you're thinking as the book has thought on this, using that technique, reduce the number of unknowns to a single unknown. You could let A, B, C, and D equal those set of values. So they've just chosen n minus 1, n plus 1, n plus 2 to be the consecutive numbers. Of course, you could choose n plus 1, n plus 2, n plus 3. It doesn't really matter. At the end of the day, this might be neat because we'll less complexity involved. We'll have some cancelling of terms. But at the end of the day, we're aiming to show that n plus 2 squared, our largest consecutive number, minus n plus 1 squared, its predecessor, plus n squared, the predecessor of that, minus n minus 1 squared, should reduce to the sum of those 4 terms together. In other words, should reduce to the expression 4n plus 2. Okay, so that's the aim. And of course, if you chose n plus 1, n plus 2, n plus 3, your aim is to show that that reduces to 4n plus 6. 1 plus 2 plus 3 is 6. Okay, so it doesn't really matter how you choose your consecutive numbers in this case. Okay. So there it is. There's our replacements. D with n plus 2, C with n plus 1, and so on and so forth. Okay, we just expand, collect like terms, and show, as we were hoping to show, that's equivalent to 4n plus 2, which of course is the same as A plus B plus C plus D. There we go. All right, I just shared that with you, just that the technique of reducing unknowns to a single unknown is really the way to go in most cases. Okay, we're pretty much done. Okay, hang on. Left-hand side, therefore conjecture proved for any four consecutive integers. Good. That's a nice way to finish it off. Okay, I was just going to do one other more complex example. Using those set definitions for complement, intersection, union, subset of, should prove that if A is a subset of B, this occurs if and only if A intersection B is equal to A. So see how you go. If you really want to, if you're over it, I understand fully. Move on to the set exercises that you'll find on Neo. In fact, I won't even go over it. This is what it would look like, assuming A is a subset of B. So X is a member of A, if X is a member of B. If X is a member of A and X is a member of B, it implies it's a member of both. Therefore, A is a subset of A and B. We now need to show that A intersection B is equal to A, so on and so forth. I'm not even going to go, you can have a look at, I'll just click through the facts. There they are, and that's how we show the first proof in that direction. So pause it and have a look over it if you're interested. If you're not, I fully understand. And then we move on to the other side. We need to assume A intersection B is equal to A and show that A therefore is a subset of B by definition. Okay, so have a close read of those definitions if you really want to. Okay, I've covered a lot of ground. So it includes all set work in exercise A and B. You'll be pleased to hear I will not bother you again for another lesson or two. Probably a couple of lessons. I'll allow you to work on it, and then we can just work on some of the set examples together as need be. An assignment is forthcoming on this unit, but before I issue the assignment, we'll have a look at proof by mathematical induction. Okay, that's all for now, folks. See you later.